Hey guys, Kenny here. So today we're going to go ahead and take a look at speed, velocity, and frame of reference. Now this is our first day in a unit going over mechanics, and we'll break mechanics down into two different units. Okay, so today we're going to be starting with speed, velocity, and frame of reference, and we're going to be looking at some pretty important vocabulary that'll take us through not just this unit, but the next unit as well. So let's go ahead and jump right in and take a look at the essential questions for today. All right, so number one, what is the difference between speed and velocity? These are two terms that we typically use interchangeably, but we need to make sure that we understand the very specific scientific or physics definitions that we're going to go ahead and use. Number two, what is the difference between a vector and a scalar quantity? These will come up not just in this unit, but in several different units that we'll cover, especially when we start looking at how we derive particular units and when we start measuring different quantities, how these are represented in terms of whether it's a scalar quantity or a vector quantity. And lastly, what is a frame of reference and how does that relate to physics? Now, the concept of frame of reference actually applies to many different fields. And so understanding what that is can have great value to a lot of different pursuits. But we also want to focus on how that relates to what we do here in physics class. All right, so let's jump right in with some of that vocabulary. Now, in physics, we use words distance, displacement, speed, velocity, acceleration. These are all things you've probably heard before, but they are associated with a very mathematical quantity. And as such, in physics, they have a very strict definition. The mathematical quantities, which are used to describe the motion of objects, or can be divided into two categories. It's either going to be a vector or a scalar. Now, these two things actually can be related to each other, and you'll see that as we kind of go through our definitions here, especially for speed and velocity. But the two categories are distinguished by one another from these particular definitions. Now let's start by examining vector definitions, because this is the one that if you've done some math, you may have already done some vectors. But we want to make sure that we understand that and distinguish that from the scalar vectors. All right, so a vector is a um, characteristic of an appropriately drawn vector diagram. It's when it has a size or a scale to it, but as well as a direction. Okay. Now, if we just simply draw an arrow, that is not a vector because the vector needs to go ahead and have some sort of scale on it. Like you see here in the upper left-hand corner, 1 centimeter equals 4 meters. Now we're doing a scale drawing like we talked about last unit. And we're going to go ahead and give a certain scale to the size of that arrow. Two, it needs to have an arrowhead so you know the direction it's going. And this is going to be a key piece that we're going to go ahead and play with when we start defining speed versus velocity. If it has a direction to it, that's going to be a vector. Without the direction to it, it's going to be scalar because scalar is still going to have a magnitude to it, but it's not going to have direction. So the combination of the magnitude and the direction of the vector is clearly going to be labeled. And so in this case, the diagram shows the magnitude of a 20 meters and is in the direction of 30 degrees west of north. And so you can see that from the diagram in the upper left. All vectors have a head and all vectors have a tail. Now, this is where it's beneficial to go ahead and know your degrees. So when you're trying to evaluate the direction, if you have some sort of cardinal direction that you're using or some other starting point, you go ahead and move your degrees off of that. Now, for me, when I think of degrees, I usually think of sports. I start thinking of things like skateboarding, snowboarding, these types of things. And if you've done those activities, you probably have some idea of this. So let's start by thinking of a skateboarder. A 180-degree flip switches the direction of the board. So if I'm facing one way and then I do a flip of the board is facing the opposite direction now. A 360-degree rotation is going to end with the board facing the same way it started. So you'll complete a full circle to get 360. And then a 90-degree turn is going to send the board either to the left or to the right, depending on the direction of the turn. If you look in the lower left-hand corner here, you can see it's kind of ticking through the different degrees, 0, 30, 60, 90, so on and so forth, and repeating that, increasing until you get completely around with 360 degrees. Now, if you've skateboarded or snowboarded, or you've done any of these tricks sort of things, maybe you ski, or maybe you just played, a video game where you did some sort of Tony Hawk skateboarding and you do like a 720. So you can go beyond a full circle. Okay, so 360 plus 360 is 720. So a 720 would be doing 2 full rotations before you go ahead and land the trick. Now, to help you kind of visualize this, I have a little clip from the X Games. It's going to go ahead and allow you to see exactly what we're talking about. Pay close attention to the names of some of these tricks. While some of the terms are a little goofy, they will talk about the degrees in this. Now, this was one of the best runs that I'd ever seen. This was the Flying Tomato, Shaun White. So we'll go ahead and watch this, and we'll come back together after that. All right, enjoy.
And see if he throws that
frontside double cork 1260.
Woo-hoo!
Wow.
That is why this dude is Shaun White. In the victory lap, he said, I'm going to put a period on it just so you think I didn't earn it, and throws it at the end.
To combo a double McTwist 1260, a trick that only 2 people on Earth can do, into a trick frontside double cork 1260 that no one on Earth can do.
That's never happened before.
Okay, so think about that.
Could this
1260.
be the highest score that we've seen in Super Pipe ever, this run, after that combo?
Whether it's scored the highest or not, it's hands down the best run that we've ever seen in history. And look at that. Lacking the amplitude that he probably wanted, and he just wanted it so hard. Cat's out of it.
Shaun got a 97.66. That's the current highest score ever in Super Pipe. Can he take himself out with this run? That was amazing in that it was the victory lap. Let's see what the judges think. Ladies and gentlemen, something big is about to happen to cap off this Winter X Games 2012.
And then he gets a perfect 100.
Perfect 100.
All right, so we'll go ahead and stop it there. But hopefully you're seeing that this is pretty impressive when you start thinking about how many rotations he had to complete to go ahead and land these tricks here. So how many times the board had to go around. Now we can think about that in terms of degrees, but as we start looking at that, it's not a perfect vector when they start talking about it, because they're not talking about which direction they're starting from in terms of trying to complete the trick. Okay, so once you understand what a vector is, remember that it has both magnitude and direction. Maybe you go ahead and watch a little bit of Despicable Me. The first movie, the villain is Vector, and he very clearly goes ahead and tells you why he's called Vector, because he's completing crimes with both magnitude and direction. So pretty cool. All right. Once you have vectors, though, you can add them together. Now, we can do it mathematically and use the angles, but a simple way to go ahead and do it, and it doesn't matter which direction or which order you use the different vectors, is using a technique known as vector addition. Now, you'll notice that in each 3 of these examples, we are doing a different sequence of adding the different vectors together. In the first one, it's A, B, C, D, E, and then you see the resultant or added vector. If you go ahead and look at the second or third example, you're doing them in a different order, D, E, A, B, C, but then you see the resultant is actually the same magnitude and same direction. So vector addition is cool in this way in that you can do adding together of vectors as long as you go tail to head, and maintain the angle at which the vector comes off. Okay, so we know what a vector is. We know what a scalar quantity is. The first term that we really need to introduce to you is speed. Now, you guys have some idea of what speed is because you've been talking about speed since you were little kids running around on the playground. So speed is simply the rate of motion or the distance covered per unit time. So when we look at speed, this is what we would call a derived unit. Okay, we talked in our last unit about things like a kilogram or seconds. These are base units. They are a single unit by themselves. But speed is distance per time. If we measure distance in meters and time in seconds, meters per second would be a derived unit because it comes from the combination of several base units, in this case, two, distance and time. And so we have a mathematical relationship that we can use to determine the speed if we know the distance covered and the time in which that distance was covered. Let's use the 100-meter dash as an example for what we're covering today. Now, I am huge into track. I really love track and field. I used to run all through high school and college. My big event was the 800, but I've run everything from the 100 meters up through the 3,000, 5,000 race. Okay. This graph shows speed and distance traveled per unit time for 100 meters. Bolt completed this race in 9.58 seconds. That's flying. Anything under 10 is super, super fast. But you'll see on the bottom, on the x-axis, you have the distance in meters, and so how much time it took to reach that point. And so you can see a graph here representing the amount of speed. It's not perfectly straight because obviously no one can keep up an exactly perfect speed. And there's definitely a pickup when you first start up because you're going to go ahead and push off out of the blocks. And there's going from basically a standstill at 0 to that initial burst of energy that goes ahead and takes you out. Now, this is part of the activity that I'm going to have you go ahead and do tomorrow on Wednesdays. I'm going to have you do a little bit of running. So hopefully you can find a nice spot. I don't need you to do 100 meters, but if we can do about 60 meters, there is a 60-meter dash, and we can kind of take a look at that in terms of how far you're going and how quickly. So before we go ahead and talk a little bit more about this, we do want to talk a little bit about how speed works, and when we graph it something like this, how we can go ahead and understand what that graph means. But before we do that, I want to go ahead and show you the world record 100 meters so you can see Usain Bolt run. This is probably one of my favorite races I've ever seen, so it's really, really impressive. So again, I hope you enjoy this. Okay.
This is what we've waited for, the showdown.
The fastest men in the world are here in Berlin. It's packed full of talent, no matter where you look.
All of the swaggering and stops.
Usain Bolt, number 1.
Who will come out on top? Who'll take the gold? Who'll take the title? The World 100-meter final. Powerful, strong, compact.
Extremely powerful and very, very quick. Oh my goodness gracious me. Oh, if that is a sign of things to come in the final, we could be in for something very special indeed. Ready. We can now look forward to a final which is going to be absolutely fascinating.
There he stands, 6'5", but his stature is such that he is a colossus over the world of athletics. Bolt versus Gay. 5 years between them. One's a world champion, One's an Olympic champion. Just 0.08 of a second between their personal bests. Less between their seasons. Usain Bolt. 40 strides he takes.
Yes,
He'll reach
yes!
speeds in excess of 40 kilometers an hour.
I'm ready.
And unless somebody's got something very special up their sleeve, he will be ready, as he suggests, to take the gold medal, I'm sure. Tyson Gay, the defending champion. The bolt is loaded. The World 100-meter final.
Set.
They get away first time. Tyson Gay right alongside Usain Bolt, but here he goes, streaking away already. It's Bolt all the way. He's looking round at Gay. Watch the clock. It's goal for Bolt. And again, he's done it again. A new world record for Usain Bolt. They say lightning doesn't strike twice. Can you believe it? He is flying.
Still gives me goosebumps to watch it.
Berlin belongs to Bolt. 9.58. Stunning, absolutely. They are adjectives which are inadequate to describe this man. He is brilliant beyond compare.
9.58 seconds. That's
He
incredible.
writes his own history with every stride that he takes.
And Steve was saying about this guy, the defending champion, Tyson Gay, 9.71 seconds. That is a new American national record. But he came a distant second behind Superman Usain Bolt.
Okay, so you can see that this is pretty impressive when we start looking at this. Now, this is our first time really going ahead and using an equation to represent a relationship to go ahead and determine different variables, whether it's speed, distance, or time. And we still use the v to represent velocity in most cases, although it's really only a true velocity if it's a vector, which means it has a direction associated with it as well. Speed is a scalar measurement, which is only going to include a miles per hour, kilometers per hour, that type of thing, meters per second. Okay, these are all scalar quantities. If you have a direction associated with it, then we would call it an actual vector, and we would call it a velocity. So velocity is a vector, speed is a scalar. Okay, and when you go ahead and drive in your car and you have a speedometer, your speedometer measures speed. So it's measuring a scalar quantity. It does not measure what direction you're going or changes in direction. It simply measures the quantity of how much space you're covering per time. Okay, distance per time, which is the definition of speed. And you should be able to manipulate those variables to go ahead and solve for any individual one: speed, distance, or time. So let's go ahead and do some practice as we go ahead and go through this. So here's your first practice problem. A car travels 300 kilometers in 6 hours. What is the speed of the car? So take a minute and go ahead and get out a piece of paper, and then you can go ahead and pause as we go through, try and evaluate this, and then we'll go over the answers. Okay. Remember from the previous slide that the equation to calculate speed is distance over time. So pause the video here and then go ahead and we'll go over it when you're ready. Okay, so hopefully you came up with an answer. Let's use our equation here. This is the relationship. And what do we know? Well, we know the distance covered, that's 300 kilometers, and we know the time in which that distance was covered, which is 6 hours. So we set this up, speed is equal to 300 kilometers per 6 hours. We do the division, 6 goes into 300, and that gives us 50. So the answer to this one is the speed is 50 kilometers per hour. Okay. Now let's go ahead and do some more. So you can have the basic idea. Let's go ahead and do two more really quick ones. All right, I'll just give you the equations. You not the equations, but the questions. You go ahead and solve them, and then we'll go over the answers. All right, so here they are. Go ahead and pause the video and try doing these two. Okay, well, welcome back. Hopefully you were able to solve both of these. We'll start with the first one. So how far can a plane travel if it flies 800 kilometers per hour for 9 hours? So we're looking to solve for distance. And so this is where I really want you to start writing down what you know first, okay? Write down what you know. Okay, so as I mentioned, we want to go ahead and write down what we know. So we know right now that we are looking for distance. So d equals something. We have the actual speed, so I'll put that as v here. We don't have a direction, but I'm still going to use v, 800 kilometers per hour. And we have our time, so t is equal to 9 hours. Okay, so when we go ahead and do this, then we can set up our equation. Velocity is equal to distance over time. This case, we're going to go ahead and solve for distance. So d equals vt. So we take our velocity and time, and that should make sense because then we can get our hour units to cancel and leave us with just 800 kilometers. Okay, so if we go ahead and do this, let's go ahead and clear this off. If we're going to use d equals vt, we have d is equal to 800 kilometers per hour. Notice I'm setting it up like we did when we were doing dimensional analysis, and we're timesing that by 9 hours. Hours cancel, leaving us with kilometers, which makes sense. That is the unit that we would go ahead and use when we are looking at distances. All right. And if we solve it, hopefully you came up with the same answer I did. When I did the math here, I ended up getting 720 kilometers. Okay. Now, for the second one, it's a little different setup, but it's the same basic idea. So down here, we're looking at how long. So this is looking for time. Okay. So when we go ahead and look at this, we can take our original equation, v equals d over t, but in this case, we're trying to solve for time. So we're going to go ahead and use t equals d over v. Okay. So we know that we have over here dvt. T is what we're solving for. Velocity is 50 kilometers per hour. And distance is equal to 500 kilometers. Okay, we can go ahead and substitute them into this equation here. So T equals distance, 500 kilometers. And then this is where you can get a little tricky. You can go ahead and do the division like this. Okay, and that's 50 kilometers per hour. But since it's per hour, this really is up on the top. Okay, so remember this is really up on the top. Kilometers are going to cancel. 500 divided by 50 is going to equal 10 hours. Okay. All right, hopefully that makes sense. So again, we need to remember that when we calculate these things, the equation is a relationship between the pieces. And when we deal with something like speed or velocity, we're going to have derived units because it's a combination of multiple base units. Okay. All right. So let's clear this drawings and move on. All right. Velocity, very similar in terms of how we're going to go ahead and calculate it. We actually use the exact same equation. The biggest difference here is making sure that we know that it has a direction. Velocity is speed with a clearly stated direction. So for example, 5 kilometers per hour is not a velocity, it's a speed because it has no direction, whereas plus 5 kilometers per hour or north at 5 kilometers per hour are velocities because they have an associated direction with them. If the motion's in a straight line in only one direction, it is the same as its speed. This inclusion of direction makes velocity a vector as opposed to the scalar that we see with speed. So let's try a question with this. It's the same math, but make sure if we're going to try and get it with a velocity, that means we're trying to include what? That's right. We're trying to go ahead and include a direction. So here's your equation. Okay. What is the velocity of a car that travels from Portland to Eugene, 110 miles in 1 hour and 30 minutes? Okay. Now assume that this is due south. Travels from Portland to Eugene. It's not exact, but we can assume for this particular instance that the derived direction is from Portland to Eugene is due south. And remember that the equation we use here is speed equals distance divided by time. So pause the video here, take a minute, try and go ahead and solve it, and then we can go ahead and go from there. Okay, so hopefully you figured it out. Let's start by simply doing the math to solve for speed, and then we can go ahead and deal with the direction portion. When we do speed, remember it's distance divided by time. We have a distance of 110 miles, and we have a time of 1 hour and 30 minutes, which is 1.5 hours. So we end up seeing 1.5 hours divided into 110 miles, or 73.3 miles per hour. Okay. That is not a velocity because it doesn't have a direction. But remember we said from Portland to Eugene, which is approximately south. So the actual answer here would be the velocity equals 73.3 miles per hour to the south. And that's how you do your velocity and speed calculations. Now we can actually start graphing some of these things. I showed you a graph of the 100-meter running distance versus time, and you can see that that's got a little, almost a line going up to the right. But we can look at two different graphs here that I'm showing you. The one on the left shows a stationary individual. They are a certain fixed distance from wherever you're measuring. And because it's flat, you can see that they're not moving. They're not going anywhere further away or anywhere closer. So in terms of the distance time graph, it's a flat section. On the right here, you can see that it's going up and to the right. This is going at a constant speed away from the point of origin. And so you can see the distance increases at a fixed amount over a fixed amount of time. And so we can go ahead and use those to understand a more complicated or real world type graph when we look at something like this. This distance time graph still has time on the x-axis, still has distance on the y-axis. And so when we start looking at this, and if we travel in that first interval we look at 4 seconds, okay, you go 4 seconds of time and you travel 100 meters. We can actually use this to go ahead and calculate a speed over that time period. You'll notice that when you get to 8 seconds, it becomes flat. At that point, the individual is no longer moving. They're stationary because their distance is not changing with respect to the point of origin. You go to the top right portion of the graph, you see in that same 4 seconds we had earlier, this time we travel 150 meters. So you see it's still going up and to the right, but this time the steepness of the graph is greater, showing that you have a greater velocity. Okay, or greater speed, probably more accurately, because we don't have a direction necessarily tied to it. Okay, now this is all well and good, and hopefully you recognize that this is dependent on where we are measuring from. This idea of establishing a point of origin for setting up our mathematical relationships is what we call frame of reference. Anytime you describe something that's moving, you are comparing it with something that is assumed to be stationary or not moving. In reality, that may not be a true statement, but for the mathematical understanding of the relationship that you are evaluating, this is true. And this object that we are using for comparison is known as the frame of reference. And we do this on Earth all the time. If we go ahead and measure the speed that Usain Bolt is running down the track, when we do that, we're marking it from the starting line to the finish line. Okay, that is our point of origin or our frame of reference. But if we were to go ahead and sit in a car and drive with Bolt as he ran, he may not seem like he's moving that fast because we're traveling the same speed. Our frame of reference shows him moving at the same speed we are, so he doesn't appear to be getting any further away. Now, you may have experienced something similar to this. Have you ever been in a parking lot sitting in your car and you look out the window and the car next to you starts backing out or pulling forward, and all of a sudden you feel like you're starting to move? You're not, but from your frame of reference, if you were thinking that car was stationary and your car is now a distance from that car, it feels like you've been moving. This is the idea of frame of reference. In other words, frame of reference is the object or point from which motion has been determined. For us, in most of the calculations we'll do in this course, that frame of reference is going to be Earth. But I need you to remember that motion is a change in position relative to that frame of reference. And this will become super important as we continue on through this semester, because as we get to more complicated mechanics problems, you'll start realizing that that frame of reference matters. Now, when you look at this picture that you see here, we forget a lot that Earth is spinning, okay, both on its axis and on its revolution around the sun. We have so many different rotations that we are just used to because we were born and raised on this planet. But in addition to the day-night revolution, rotation, that we have on our planet and the yearly revolution around the sun, we have to remember that our solar system is also moving around the center of our galaxy. Okay, so we are in what's known as the local arm, and that local arm is between the Sagittarius and Perseus arms, and that is going around a circle around the nuclear bulge or supermassive black hole at the center of our galaxy. And it doesn't stop there, because remember, our galaxy is actually flying through space as well. So we're talking about motion on top of motion on top of motion that we don't even notice most of the time. So I want to try something really quickly. I want you to close your eyes. Okay. When you close your eyes, hopefully you're doing it right now as you're listening to me, I want you to slow your breathing down, turn off all sounds around you if possible, and just sit there for a second. Can you feel all of that movement we just mentioned? It's pretty crazy to think that we're doing that much. We're flying, hurtling through space, which is why we are so fortunate, because our planet is always in jeopardy of some major cataclysm of something colliding with us and causing huge damage to the planet, but we're not. Okay, so if you ever get a chance, I encourage you to go ahead and do some of that nighttime star watching or sky gazing. And if you have a camera that can do it, or a video camera, you might try doing some of this time lapse. I have a short little video here. I probably won't play the whole thing, but if you're interested, there are plenty of them on YouTube that goes ahead and does a time lapse of stars. So I'll leave you with this, and then we'll go ahead and call that the end. Hope you guys have a great one. Take care of yourselves. Just chill out to some time lapse of star movements. around us in the heavens, and that each of those points of light represents a star or a planet that is moving on its own, and so those positions are not always going to stay the same. Okay, I'll go ahead and stop it there. You guys can always go ahead and look this up on YouTube. Era of Time, time-lapse photography. Okay. All right, you guys, take care of yourselves. Have a great rest of your day. Take care. Bye-bye.